Got another exam question walkthrough for A-level chemistry. So this is number 12 in the Redox Titrations playlist. Just a short question, this one. So there's a nice little question on the Fe2 plus MnO4 minus titration, and then it moves into electrode potentials. Question suitable for all of the major exam boards, and if you haven't already subscribed to the channel, I'd love you to do so because it really helps me out. And as always, the link to the questions in the description of the video if you want to try it first. Okay, so make a start. So for the first part, we've got to state the colour change seen at the end point of the titration. So I'll just quickly explain this. We've got potassium manganate 7 in the burette, that's purple in colour, and we've got the aqueous Fe2 plus ions in the river water. So obviously, as this reacts with this, the purple colour will be decolorised. Once all the Fe2 plus is gone, this has got nothing to react with. So that one drop of MnO4 minus that's going to go in at the end point doesn't have anything to react with. So it will be a sort of very pale pink colour, or you could say pale purple. What you're not allowed to say is purple, because obviously one drop of this in this volume wouldn't be purple, it would be too dilute. Moving on to the next part, so the three titre is just the final minus the initial. So we've got 12.65, 12.95 and 12.75, and the titre needs to be the average of the concordant results. So the concordant results are those within 0.1 cm³ of each other. So obviously 1 and 3 are concordant, so we're ignoring titration number 2. So the answer is 12.70 centimetres cubed. Now the calculation, really easy one, this one, I hope you don't mind me saying that. So the first thing we've got to do is work out the moles of MnO4 minus ions that we're using in the titration. So that's concentration times volume, that's that mean titre in decimetres cubed. So there's that many moles of MnO4 minus. Next thing we do is apply the mole ratio to get the moles of Fe2 plus that were in the 25 cm³ of river water. So it's a 1 to 5 ratio, so there'll be 5 times as many moles of Fe2 plus, so that much there. And then all we've got to do is work out the concentration of the Fe2 plus ions, so in other words, how many moles per decimetre cubed. So we take the moles and we divide by the volume. So these moles were in 25 cm³, so we're dividing by 0.025 dm³, and we get that. So moving on to part B now, the first thing I'll do is look at the reasons for step 1 and 2, and then we'll finish off by using the electrode potential information in the table to explain why that happens. So reason for step 1, so what's happening in step 1, excess zinc has been added to a sample of the river water and warmed gently. So what is the purpose of that? Well, it's going to reduce the iron 3 plus ions in the river water down to iron 2 plus. Moving on to the reason for step 2. So in step 2, they've cooled the solution, removed the excess zinc by filtration. So why have they done that? Well, if any zinc was left in the reaction mixture, the acidified potassium manganate 7 would oxidise it up to zinc 2 plus. So moving on to the explanations now. So you'll notice I've put a forward arrow on system 2 and a reverse arrow on system 1. So why have I done that? Well, the electrode potential value for the iron 3 plus 2 plus system is more positive than the zinc 2 plus zinc system. So the system 2 will move left to right, or forward you could say, meaning that the zinc 1 will go backwards. So you can see what's happening in that process is the iron 3 plus is being reduced to iron 2 plus. So I'll write that up, and I'm going to also write an equation just to back up what we're saying. So all I'm saying is the electrode potential for system 2 more positive than system 1. System 2 is therefore going to shift to the right, system 1 is going to shift to the left, and there's the equation that accompanies that. I've doubled the iron species because there's only 1 electron involved in its half equation, whereas there's 2 in the zinc one. And then moving on to the explanation for step 2. So again, I've drawn a couple of arrows So the MnO4 minus H plus system 3, that's going to move forwards or to the right because it's got the more positive standard electrode potential. The zinc 1 obviously is going to be forced to go in the reverse direction. So if any zinc was still in the mixture, the zinc would be oxidized, but what we want to happen is we want the iron 2 plus to be oxidized to iron 3 plus. So we need to get rid of the zinc. And then the same style answer as before, so just saying electrode potential for system 3, more positive than system 1, system 3 shifts right, system 1 shifts left, and there's the equation. Quickly explain the numbers. We've only got 2 electrons in the zinc half equation, but we've got 5 in the manganese one. So all we've got to do is get them both up to 10. So multiplying the zinc equation by 5 and the manganese one by 2.